Hello everyone, my name is Reali and I'm from the Universidade de São Paulo in Brazil. It's a pleasure to attend this event, the first Latin American Summer School on Cognitive Robotics, LACORO 2020, and I would like to thank the organizers for inviting me. The title of my talk is Scaling Up Reinforcement Learning with Transfer, and I will present part of the research that my students and I have been conducting in machine learning. Let me first introduce myself quickly. I'm from Brazil and my city, São Paulo, is right over the Tropic of Capricorn. Here in São Paulo, following the Pinheiros River, we arrive at the Universidade de São Paulo, USP for short. USP is located at a very large green area in the city of São Paulo, on the banks of the Pinheiros River on the west side of the city. I'm a full professor at the Computer Engineering Department of the Escola Politécnica of USP. In this slide, we can see a photo of the part of the USP where the Escola Politécnica is located. During my PhD, I spent 2 years as a research scientist at the Karlsruhe Institute of Technology in Germany, working on computer vision, intelligent robotics, and machine learning. A few years later, I was a guest researcher at Carnegie Mellon University, investigating planning, execution, and learning for multi-robot applications. Currently, I'm also the director of the Data Science Center of USP, C2D for short. C2D is founded by one of the largest banks in Latin America, the Itaú Unibanco Bank. The goal of C2D is to produce cutting-edge research and to train people in the field of data science, machine learning, and artificial intelligence, fostering the area's ecosystem in the country. In particular, my research question is, can we design agents capable of learning from experience and from other agents and reusing knowledge to improve their performance? In this talk, I will give some basic concepts of reinforcement learning and transfer learning. Next, I will describe some of the research we have done on the use of transfer learning in reinforcement learning, in particular the use of a device from other agents, the reuse of knowledge learned from other tasks, and the use in curriculum learning. I will conclude by showing some applications in which we have employed reinforcement learning. Let's start with some reinforcement learning concepts. Reinforcement learning has some features like the feedback the learner receives is delayed and occasional. Time here really matters because data is sequential and non-independent and identically distributed. Agent's action affects the subsequent data it receives, and the agent learns via experiences, by trial and error learning. The task of an reinforcement learning agent is to learn from this delayed reward to choose sequences of actions that produce the greatest cumulative reward. Reinforcement learning allows us to deal with sequential decision problems. To understand how reinforcement learning works, consider an agent that wants to learn to ride a tricycle. Reinforcement learning is based on an agent that learns from the environment by interacting with it and receiving rewards for performing actions. It works like that. At each time step, the agent observes the state of the system. For example, it observes the position and the speed of the tricycle. Then, the agent chooses an action and applies it. For example, it decides how to move the handlebar and pedals. The system then evolves to a new state and the agent then observes the new state and receives a reward. In our task, this reward could be the advancement of the tricycle, for instance. The interaction cycle repeats and represents an experience performed by the agent, given by the current state S, the action A applied to the state S, and the next state S prime and the reward R. These steps are repeated over and over again, and the agent learns to improve its performance with the many experiences it has. That is, the agent learns for each state the action that produces the highest expected accumulated reward. This is given by a policy pi that maps states S into actions A that maximizes the value Q that represents the expected discounted sum of expected reward. The optimal policy then is given by the action that maximizes the optimal Q function for each state. We have two types of procedures in reinforcement learning. One that estimates the Q value function and then calculates the deterministic policy to be followed. And another that directly estimates a stochastic policy and defines the action to be performed by sampling this policy. One of the first value-based algorithms is Q-learning. It is applied in environments that are fully observed, stationary, single agent, and with discrete actions. Q-learning iteratively estimates the Q function with each experience the agent had in the environment, as shown in this equation. The DPQ networks algorithm, known as DQN, uses a deep neural network to model the Q function. The network is trained with the quadratic error loss function. The network has the state as input, which can be continuous, and the Q value for that state and each possible action as outputs. The disadvantages of DQN are that it cannot handle continuous action spaces and it cannot learn stochastic policies. However, with deep reinforcement learning methods based on policy gradient, we can learn stochastic policies and handle continuous state and action spaces. Now, the neural network has as outputs the probabilities of executing each action in that state given at the network input. The DQN may fail with complex Q function, but the policy gradient methods can still learn a good policy. Policy gradient has faster convergence than DQN, and the policy gradient can learn stochastic policies while DQN only learns deterministic policies. Policy gradient can handle continuous actions and the DQN cannot. However, policy gradient needs more data than DQN, and it is less stable during training than DQN. So, reinforcement learning is a very powerful tool. However, it requires many samples to learn, and it takes too long to learn. And the solution can usually only be applied to one specific task. This makes reinforcement learning very inefficient. We can improve learning with transfer. To give you an idea of what I mean, let me give you a simple example. Suppose we know how to ride a tricycle, and suppose we want to learn to ride a bicycle. The question is, how would knowing to ride a tricycle help in learning to ride a bike? And besides, to use instructions or advice from other agents to improve learning. In order to better exploit the agent's previous experience and the knowledge provided by other agents, we have been investigating several ways to use this knowledge in learning new tasks in a reinforcement learning agent. Knowledge transfer can improve learning in three aspects. It can promote offset improvement, that is, to start learning with better performance. Speed improvement, that is, achieving a certain performance using less training data. And generalization improvement, that is, to achieve even better performance with the transfer than it would have done without it. We are investigating the use of advising from other agents, the use of knowledge from previous tasks, and curriculum learning. For that purpose, we define a general architecture in which the agent can interact with other agents and also access and update its knowledge base. Let us focus on the problem of a learning agent interacting with other agents, requesting and providing advice. Our proposal for this problem is ad hoc advising, which is an adaptation of the Torrey and Taylor's teacher-student architecture. It is a flexible architecture that can reuse expertise of humans and trained agents. In our proposal, advisors do not need to be experts and advisees do not need to be constantly observed. In our proposal, when the agent comes across an unknown situation, it can ask for help, assuming the role of advisee. If agents are not confident about their knowledge, they may not respond. Or, if they are confident in their knowledge, they may act as advisors and suggest actions to the advisee. We control the agent's actuation during the learning process through advice given by an agent with more knowledge of that part of the task. In our proposal, we have two types of confidence functions to guide the decision to give or ask for advice. Ad hoc visit, in which we use the number of visits in that state to measure the confidence level to ask or give advice, and ad hoc TD, in which we use the value function together with the number of visits to define the degree of confidence. In our proposal, agents trust the advice received and there is no conflicting advice, and they have a budget to spend on requests and advice offers. We have compared our two proposals with the original teacher-student architecture, a system that always shares successful episodes, and with a system that does not use advice, that is our baseline in black. We conducted experiments in the half-field offense domain. The graph at the top of the slide shows the number of goals per training episode, and in the bottom graph, we show the use of budget per training episodes. And results show that ad hoc advising performed better than the others while using less advice. Now, let's look at things the agent can explore from its own knowledge. We here show two approaches, intertask mapping and an approach based on case-based reasoning. Let us first explain intertask mappings. Suppose we have a previously learned task the source task on the left side of the slide. And somehow it is similar to the new task we wanted to learn, the target task on the right. The question is how to relate both so that knowledge from the source task can be used in the target task. In previous work, this intertask mapping was done manually. We propose an automatic method to define a probabilistic intertask mapping, which quantifies similarity relations between the source task and the target task. We use object-oriented Markov decision process to describe tasks, and we explore this representation. Our method is named Python. We weight initial Q values in the target task according to Python. Let me give you an idea of what an object-oriented Markov decision process is. It has classes that define the types of objects and they are described by a set of attributes. An object is an entity that belongs to a class and has values for each attribute. For example, in this gold mine domain, we have 3 classes: miner, gold, and wall. And the state shown in the left side of the slide is described by 3 objects of the class miner, each one with attributes of grid position, X and Y, and so on, as is shown on the right side of the slide. Each object in the source task is mapped to several possible objects in the target domain, establishing a mapping probability between each target and source domain. Here, we showed results of the comparison among the regular learning from scratch, the learning with transfer using a manual mapping, and our proposal, Python. We can see that Python is much more effective, having offset, speed, and generalization improvements. Python completes the task in fewer steps. Let me now explain our case-based reasoning approach. Another way to reuse knowledge is by using DECAF that combines case-based reasoning with deep reinforcement learning. It follows the CBR methodology, which is similar problems have similar solutions. In case-based reasoning, we have previously learned the cases in a library consisting of tasks and their respective solutions, given by policies. Given a new task, we retrieve from the library a set of similar cases. Then, we use this subset to suggest an actuation policy. We verify and fine-tune this policy in the revise steps, and in the end, if the results of that policy are good and it is dissimilar to the policies in the library, we retain the new task and its respective policy in the library. DECAF stands for Deep Case-Based Policy Inference. The basis of DECAF is the A2T architecture, where we have 1. The case library, 2. the current learning task, and 3. learning weights to select among policies, current and previous ones. And then the architecture decides which action to apply at each moment. Here the retrieve and reuse phases are merged and there is no revise phase in DECAF. Results shows that DECAF, the blue curve in this graphic, performed much better in this Atari domain when compared to the A2T architecture and to the original DQN architecture that was used to learn Atari games. We can also see in these bars on the right of the slide that the time spent by DECAF to start consistently winning the games was much less than that of the other approaches. We also investigated the composition of tasks in a curriculum. Curriculum learning for reinforcement learning has been an active area of research in recent years. Its principle is to train an agent on a defined sequence of source tasks, called curriculum, in order to increase the agent's performance and learning speed. We use a curriculum in two situations. First, in faster overall learning, when we wanted to split a complex task into simpler tasks in which learning is conducted, and in the end, the total learning time from scratch in the complex task can be reduced by sequential learning in increasingly complex tasks. And then also when we use a curriculum when we wanted to spend less time in complex tasks, that is, when it is dangerous or too costly to learn directly in the complex task. Our proposal is to use object-oriented task description and then to build a curricula as graphs, and finally to provide a way to skip tasks in big curricula. A task is described as an object-oriented task T, where C represents the classes, O is the set of objects, S0 is the initial state, A is the set of actions, T is the state transition function of the environment, and the R is the reward function. In the grid word domain, in this example, we have 5 classes: agent, treasure, pit, fire, and env. In the state S0, represented in the left side of the slide, we have 4 objects: miner 1, pit 1, treasure 1, and env. And the values of their attributes are: for miner 1, the attribute is its position, here 1, 1. Pit 1 is in position 1, 2. Treasure 1 is in 2, 1. And the environment is defined by its size, here 2 by 2. This is the same representation we used in Python. Our idea to automatically build a curriculum is to decompose the target task into several simple tasks which are represented in a graph. The use of object-based representation facilitates the composition. For example, consider a grid world consisting of agent, treasure, pits, and fires. On the left is the target task, and on the right is one of the possible tasks derived from the target task. Each simple task has a transfer potential. Based on the object-oriented description, we can calculate the transfer potential among tasks. The transfer potential function prioritizes tasks that they are similar to the target task and that they are dissimilar to the tasks already in the curriculum and that are also smaller than the target task. Starting with the target task and gradually decomposing the tasks, we build the curriculum graph. During the decomposition of tasks, we choose those with the greatest transfer potential to compose the graph. Once the curriculum graph is built, we go through the graph to mark the tasks that should be learned in the curriculum. As the target task must certainly be learned, we start the traversal with it. The path in the graph starts backward from the target task and selects simpler tasks tasks with great transfer potential. Finally, the loop of the procedure is like that. We select a marked task T with no marked children. Then, this task T learns for a specific time reusing previous knowledge, and we then unmark T. This is repeated gradually until the target task learns using all the knowledge learned from all previous tasks. To evaluate our proposal, we compare our system with two other approaches: Svetlik's proposal with manually given source tasks, OO given, that is an object-oriented curriculum with manually given source tasks, and OO generated, that is our proposal. The baseline is a non-curriculum learning approach. We use two domains, a grid word domain and the half-field offense domain. In the grid word domain, we can see that both OO given, the orange curve, and OO generated, our proposal in green, achieve a better speed performance than non-curriculum. And here we presented results for a more complex task, the half-field offense domain. None of the curriculum approaches converge faster than no curriculum, but they need fewer steps in the complex task. Finally, I would like to show you some applications that we developed using reinforcement learning. We proposed an energy management system for smart homes in a smart grid environment. In a smart home, we have a microgeneration of energy given by solar energy, for example. We also have batteries to store energy. We take energy consumption into consideration, and the smart home has access to the power grid, from which it can buy or sell energy according to the energy price given at that moment. The energy management system uses batch reinforcement learning to learn the policy that decides whether to buy, sell, or do nothing at a certain moment, depending on the demand, the price of, and the amount of energy generated and stored. Our results show an increase in the financial profit when compared to the naive grid policy. The increase is more than 20% in Brazil that uses the time of use tariff, and more than 14% in the US that use the real-time pricing tariff. We also apply distributed multi-criteria reinforcement learning in a multi-agent scenario to charge electrical vehicles. Our proposal makes minimal assumptions regarding the distribution grid, works under any type of tariff, and can be configured to follow consumer preferences. Our proposal is MASCO, a multi-agent selfish collaborative architecture that aims at simultaneously minimizing energy costs and avoiding transformer overloads while allowing electrical vehicles recharging. We performed experiments with real energy prices and empirically show that MASCO succeeds in balancing energy costs and transformer overloads. Deep reinforcement learning was used here in a task-oriented dialogue system. The dialogue system is composed of a module of natural language understanding, a dialogue manager module, and a natural language generation. The objective here is to control the dialogue in the dialogue manager using reinforcement learning, in order to increase the success rate while decreasing the number of interactions with the user. So, we have a lot to do. We believe transfer learning is a key component for scale-up reinforcement learning, and reinforcement learning agents should take advantage of all available knowledge sources. Our ongoing and future works include to integrate multiple approaches into a single framework and to explore languages to represent problems and solutions so that we can automatically discover similarity between problems and solutions. We also wanted to deal with real-world problems. I would like to thank my students, contributors and funding sources for these achievements, and thank you for attending my talk.